Okay, so now we're really getting into chapter 18. I had this basically same introduction last time, but that was to motivate why we were doing chapter 18, which is extending. We're extending this in two. You can think of this in two different ways, right? Think of it like we're extending particles to rigid bodies. Well, particles, we already talked about kinematics and kinetics, right? Kinetics was force, mass, acceleration relationships, work, energy, impulse, momentum, right? We already did that for particles, so that's the extension going on here too, right? Another way to think about this, we already spent a long time talking about the kinematics of rigid bodies, right? And so with the main focus there being on rotational aspects, because the translation is a trivial extension of particles. But now we're extending this to the kinetics, right? So now we're adding in to our kinematics of rigid bodies in chapter 17 what the force, mass, acceleration, work, energy, and impulse, momentum extensions are for, two-dimensional motion of three-dimensional rigid bodies, let's say, right? Okay, so now we're really getting into it. Last time we had to talk about this new geometrical property we need to introduce the ideas here, which is the moment of inertia and the center of mass. And so now let's just have a arbitrary shape, and this is just pure motivation, right? So let's remember G is our center of mass at point G. That's the way, the book notation, that's what I'll go forward referring to them both ways. Now we could have a force acting on this like body. We could have a moment acting on this body. Forces cause translational motion. And it turns out what we're going to get to is that moments cause rotational motion. Okay, our goal is, and we'll get to this, right? This is basically Newton's second law as we know it. The forces cause translational motion. Forces cause accelerations, linear acceleration. Our goal in this lecture today is, goal for this lecture is to develop the equation of rotational motion that is basically the rotational version of Newton's second law. This is Newton's second law here. Well, we're going to write it down in a second. And so, having said that, this lecture, this video, is going to feel like one long derivation. But it'll have important stepping points along the way, and important in that once we get to final results, there's going to be a lot of different forms of them. We really need to know through the derivation like what each individual term means, and when we're in a particular case of planar motion versus a different planar motion. When should we use planar motion about a fixed point versus about the center of mass? We need to work through the derivation to be able to talk about those different forms and what the different symbols mean in the equations. Before we get there, I just want to mention we use the word moments here. You might also hear these talked about as couples, or actually in physics they talk about these more as torques, forces at a distance. We don't use torque too much in engineering, but moments and couples are used somewhat interchangeably. There actually is a difference, right? Couples are actually a result of two forces that act opposite each other but at a distance, right? So you got two forces like that actually is a couple, whereas a moment is more of a rotational imposition, right? It's actually a force that directly causes a rotation. Well, either way, we can use these words interchangeably. So just know that we're doing that. Okay, so let's get into it. Again, we're going to take this step by step, and hopefully it doesn't last. We'll get through this as quickly as possible, but in order to achieve the goals, which is to develop this equation of motion, and then to have a full discussion on what all of the parts mean, and that comes in through the derivation, right? Okay. So our study of dynamics of rigid bodies is going to come in the same general way that we talked about dynamics of particles, which is force, mass, acceleration that we see here. and then work energy, and then momentum. All right, talking about momentum. Chapter 18 just focuses on this relationships, the direct relationships between force, mass, and acceleration. In order to apply that, and so next time we'll have just examples of this, which hopefully should clear up some of the confusions or some of the complexities of the derivation here. You know, when you go to apply it, you know, oftentimes that's where you're actually like, oh, okay, well, you know, I'm actually learning it. But this all stems out of this. What we're trying to get to is this relationship between force, mass, and acceleration, but for the rotational version, because I think we got it for translation. So let's remind ourselves, give us a nice translation, and this is what I said. We're going to talk about Newton's second law here in a second. That's right here. Translation, our equation of translational motion, truly is sum up the external forces. You get the mass of the object times the acceleration of its mass center. Okay, that's what we mean here. Acceleration of the center of mass. Okay, and so what I mean, a trivial extension, you know, of particles is right there, right? Slap on the G that represents the center of mass of this object, and we've got translation done, right? Which is one aspect of kinematics, right? The translational component. The other one that we spend more time on now is rotation. And okay, so we do need to pull some things back from when we introduced rotational motion in chapter 17 here. Okay, so recall, and in fact, the first time we saw angular aspects was previous to this, previous to chapter 17 too. Angular momentum really came from, is the really definition of what angular momentum is. It's the moment of linear momentum. Okay, so we've already seen that, and we gave it a symbol. Okay, the symbol for angular momentum was h, and about point O, right? So we have to take a moment. We have to do the moment about some point, or at least some axis here. The angular momentum about axis O here is the moment. So the distance, the position vector to go from point O to you know, the location of interest here, crossed into the linear momentum. Okay, now this is for particles. Okay, this is when we talked about this. So for particles, we had mass accumulation at a point. So it had some, you know, it had a mass, a finite mass, and or a non-zero mass, and it was all accumulated at a point. That was at least the assumption. I mean, it's not practical, it's not real. But this right now should all be reviewed from previously, right? Just the definition of what it was for a particle. Now, if we get into rigid bodies where we have a mass distribution, we then need to think about this as a differential angular momentum for a differential mass element. Okay, so for a differential mass element, we have a differential contribution to the total angular momentum of an object is r cross v dm, right? Just take a differential mass, it has a differential contribution to the angular momentum. So let's get a picture. Let's say our coordinate system is down here, and let's draw our shape. And this shape is composed of a whole bunch of these differential mass elements, little cubes, because we have a Cartesian coordinate system that we've chosen. All right, so there's dm. And this also shape will have a center of mass, and let's get it nicely separated. Maybe it's heavier mass down here, or maybe there's more volume into and out of the page that pulled it a little bit downward, but regardless, let's just say that the center mass is there. Okay, so then we can define our position vectors, right? So the position vector from the origin to dm is r, and that's what you see here, right? It's position vector. And then that little dm could have a velocity, right? And I don't know what that is, right? Could be anything, so I'm just making this up as we go. And yeah, so that's it, right? That is the contribution to the total angular momentum for the object from that little dm is given by that. Take its position vector to get to dm from the origin of the coordinate system of choice, cross it with the v, right? So v cross r, you'd get some, rotational contribution about the origin from that little element, there, right? And you do that for all the other shapes, and you could get the total, right? That's what we'll do next, right? So integrate this. Integrate to obtain the angular momentum NLAM for the entire body about O. Right? There's always a whenever these angular attributes, angular momentum, moments, it has to be about some chosen point or at some chosen point or about some chosen axis, right? So we're accumulating all these. This is just going to be integrate over the entire mass of the individual contributions. Okay? So now, what we'd like to do now is relate this to the center of mass. Again, we talked about last time how that was going to be a convenient choice often because, well, you can see up here, right? Our acceleration is of the mass center. Our translational kinetics is all about the mass center. So we want to now to relate this to not about this point O, but how does this relate to the angular momentum about the mass center? Okay, so then we need a relative position. Okay, a relative position, R, right? Different way to get to R is to start at, well, to go from the origin to G, the center of mass, and then add in the relative position to dm from G. Okay, so that's going to look like this, right? We could either go directly to dm, to the dm from the origin, or we could go from here to the center of mass, and then from there to dm. So this here is r G from O, and this is the position vector to dm from G. And I'm just labeling dm as our current one. Remember, we're accumulating all of these over the entire object. Okay, so that means that now we have our total angular momentum, h naught, is the accumulation of the position vectors. Oh, I forgot to cross it with v. Cross v, I guess I could have fit it in there, dm. Okay, so I say accumulation, but this is always the same. That's the thing that's going to change, right? So the position vector for all of the little dm's in the entire thing, right? The position vector to the center of mass from the origin, that doesn't change. The center of mass is constant for the entire shape. I mean, it's a global property of the object. So that thing, it is not, the accumulation comes in those v's there, and this is over the entire mass. And then we do a term over here. Now these change, right? The integral are the position vectors to dm from the center of mass crossed into v dm, right? So it might look like we're making things more complicated, but let's see, what do we have here, right? So total angular momentum for the whole object about point O there. This is now the angular momentum of mass center about O, right? Because the position vector is G. And this is our angular momentum of mass. So what we're doing is accumulating all the dm's about G. All right, so this we can call the angular momentum about point G, right? And there, hey, we're getting a relationship. Let me rewrite that. Hg. Okay? We now are relating the angular momentum about O to the angular momentum about G. Right? Okay. So, yeah. Let's keep going now. What we now next need to do is relate this velocity. That's the absolute velocity here. Can we relate that velocity to the velocity of the center of gravity, right? Or of the center of mass. All right, this is the acceleration of that mass center. We now want to extend this to not just the position, but also the relative velocities as well. Okay, I'm going to keep this page nearby because we might need to refer to it, but I'm moving on to the next one. Okay, so now we move into relative velocity. Okay, and what this says, right, is that the velocity of our dm, right, that's the little differential mass element, Well, that's on a rigid body, so we can take that as the velocity of the center of mass, the mass center, and then add onto it the rotation of the object crossed into the relative position of dm starting from g, or with respect to g. All right. Now here, this is, by the way, this whole stems from, this is the relative velocity of dm with respect to g, where dm and g are on the same body. So that's what allows us, we're 2 points on the same body. That's what allows us to write it, the relative velocity, with just an omega, right? With just an omega of the body. Okay, so let's see if we can, the next step, we could either break this down into a bunch of different, it's really from the definition of what the center of mass is. I do need to pull this back in here right now. Right now we have h naught, one way to represent the total angular momentum about O, the origin of the coordinate system, or that axis that could be anywhere, is the angular momentum about g, right? So that's how much rotation we have if g is the center, right? As g is the point. And then we have this extra term here. All right, this is hg. This is the term we have here, right? Well, by plugging this into here, okay, let's see, we have these like position vectors of rg. Well, that could be pulled out, and v. Well, this term could inevitably be written as, this can be shown vg. Okay, so all we've done here is we've just thrown out a term, okay, which is this term. Okay, so to go from here, oh, it's a little bit off. To go from here to here, we've thrown out this contribution there. Okay, so let's see there. Let's look at that term. We canceled out, it's not really canceled, we set it to 0, a term that looks like this. M R G from O crossed into this component, omega cross R dm g dm. Or another way to think of that, another way to write that term is integrate over the mass rg crossed into the velocity relative dm relative to v. Okay, so without ever going to the, I'll tell you, the math like works itself out, right? You can work through the math here, and you can say that this equals 0. But what we're actually doing here is saying, okay, well, this can be pulled out of the integral. So even better, we could say this equals rgo, and that's because that's constant for the whole object, right? That doesn't change as we go to different parts of our mass, because this is the relative position of the center of mass from the origin, right? That's going to be the same for all of the little dm elements as we go about the whole thing and integrate it, right? That's always going to be this green arrow right here, right? So let's pull that out and cross it with the integral of v dmg as we go to all those different elements. Okay, well, this isn't 0. So if this whole thing is going to be 0, that has to be 0. Why is that 0? Okay, well, this is now the relative velocities of all of the individual dm elements as from the center of mass. Okay, so think about an object with the center of mass there, right? Basically, it has equal mass in all directions, and we're going to weight that mass by looking at the velocities. Well, if this thing is rotating, right? By the way, the velocity here is just going to be its rotational motion, right? Which is what we have here, right? I just replaced it here so we could just talk about the relative velocities. This is the relative velocity of all these like little dm elements, and these dm elements are all around it throughout the entire shape, right? Well, let's say the whole thing is rotating right now with a positive omega, right, in the right-handed coordinate system here. So if that's the case, well, then the further you go out, the bigger this is. But hey, that has a neighbor over here that cancels that out. And then this term over here, maybe it's not going as fast, but that has a neighbor that's right there. And this one over here has a big component that's like there, but that has one over here that's canceling out. It might not have a perfect partner, but it, in the integral, has partners that are all canceling them out, Right, so the velocity vector always has a neighbor over here that cancels it out. And that's why, just hand wavy, this term equals 0 and we can throw it out. Okay. Whether or not we're satisfied with that explanation, I mean, I am. I think the visual is great. This is where we're at right now. And just let's just check in, because I need a breath. Take a breath here. This says that we got our angular momentum of the entire mass about the center. Angular momentum of the mass center about O, that point here. Okay. We then have that equals the angular momentum about the center of mass, which is right there. Then we have this added term that is the relative, well, it's the position vector to get to our center of mass plus mvg. I mean, and this is the velocity of that center of mass. So we've now this is it. Like this is a general description of the angular momentum of some arbitrary point to everything now written in terms of the center of mass location multiplied by the position vector, the relative position between the two. Right? So that's pretty powerful. We've already made a huge step of the way there. In fact, this is the general. I don't know why I squiggled. There should be a big box around this, because this is a general description of angular momentum. Right? By the way, we haven't talked about kinetics at all. That's not even here yet, right? Next step is we want to restrict this to planar motion. Restrict to planar motion. And that means that we'll only say, hey, this is only happening in 2 dimensions. So 2D. Okay? And in order to, what we're imposing there on the math is that the angular velocity is in the k-hat direction. So we're choosing k-hat for this to be true, because there's only one axis, by the way, right? Then our position vector from dm to g, well, we'll get to this in a second. Well, I can write it down. We're going to have to define this here in a second. What we want to do now is write the angular momentum about the center of mass, which we derived along, or well, it was a term along the way. It's actually this term here, which is that term there. We just called it hg. We now want to plug in that relative velocity there. Okay, that relative velocity is the velocity of the center of mass plus this rotational, the relative velocity to get for dm compared to g. Okay, so this now is the position vector dm from g crossed into that relative velocity omega cross r dmg. Okay, dm plus, so I'm switching the order here, plus m r dmg crossed into the velocity of g dm. Okay, for the same reason that this term was 0, this term was 0, I mean these are all equal to each other, this term is going to be 0 as well. Should we hand wave our way through that again? I mean, this is a little bit different, right? Again, this guy doesn't vary. Doesn't vary with each differential mass element. So that can be pulled out of the integral. So we can think of this whole term as an integral of r dmg. That's the relative position of each dm little mass with respect to the center of mass. Integrate that over the entire body, and then cross that with that constant vg, because this is just that velocity of g. That's going to be the same for all of our mass elements. Okay, this term is what gives us 0, right? This is basically, right, so think of this. This is now, take your object, take your blob, there's our center of mass, and this is now relative position vectors to go to each little dm. Remember, each dot in here would be a dm, and you're accumulating all those, but you're accumulating the position vectors. So you got that one going over there, well, that's canceled by something going over here. And you got this little one over there, and that's canceled by that little one over there, and you got maybe a big one to go out the outside and a big one going on the outside, right? And again, it's maybe not a perfect, maybe there is an element out here that doesn't have a perfect partner, but because of the definition of center of mass, there'll be in accumulation canceling ones over here, like as you add them all up. So this term equals 0. Okay, again, hand wavy, but you know, we can go through the math, but I think it's really nice to see it in like the visual look of it. Okay, so what I now want to do is write, I want to write this in terms of something that can help us calculate this, because this term is now 0. Okay, so this term is 0. So we just got this term left. Okay, how are we going to write RDMG, which I know we accumulated all the way here? Well, you can see these are all radial lines, right? As we see them here, these are all radial. Let me do another picture. It's going to look just like this. So there's our coordinate system. Put our blob here. There's G. Okay, and when we go now to a, let's actually put in a DM here. DM. Now this, the relative position from G to DM is right there. There's R DM from G. That's always going to point in the direction if we choose to do like a tangential. Well, or we could do radial. I mean, they're the same. Yeah, let's do that. Let's just call this radial component, right? That's always in the radial direction if we choose to think about it or analyze it right now as a polar, right? And by this definition here, right, the rotation here must be in that k direction. So if we're imposing planar motion, so it's rotating this way. Okay? And so we can do this. So we can come up here and say, okay, well, then this relative position vector, we'll just call this whatever r is for that dm, er. And we'll always have like you know, from the g's perspective, this is a polar coordinate system, right? Who cares that in the primary reference frame it's a Cartesian coordinate system, but in g's perspective, which we need for the position vector to get to dm from g, we'll use a polar coordinate system. That's just going to make our lives easier. Okay, so now hg, right, I'm going to come back to here. That is r crossed, rer crossed into omega k hat crossed into rer. And by the way, this isn't polar, this is actually cylindrical coordinates, right? Because we have that third dimension. Okay, now let's look at this, right? So this is going to be integration over the entire mass of, well, omega and r we can kind of pull out and just treat so we have an omega r squared in terms of what we're multiplying, but the cross product matters here, right? So we still have that er there, but what's happening in the middle here, I'll keep the parentheses as they were, it's just k hat cross er. So k hat comes out of the page, wrap your fingers in er, that's in the e theta direction. Okay, and then we have er crossed into e theta, that's er that way, crossed into e theta, that should be a k hat. All right, so then this is now omega can be pulled out of the integral, that's constant for the entire shape because this is a rigid body. The k hat can be pulled out, well, that's just a unit vector. What we can't pull out is the r squared dm. Okay, that's an expression for the angular momentum about our center of mass. Omega k hat integral of r squared dm. Does that look familiar? Right? This would be a great time to say if anyone in the class recognizes this. Well, we don't have that luxury here. This right here is the moment of inertia that we talked about last time. So this is our moment of inertia about G, about the center of mass G. And we call this a IG. Okay, and this can be any coordinate system you want. We just chose the polar coordinates to do this, but you know, this is just what it is. Okay, so we're ready to say that our angular momentum about the center of the mass is always the moment of inertia about the center of mass, omega k hat. This is our angular momentum about the mass center with polar, so we have a planar, with planar rotation, planar motion, right? If we are limiting it to that. We don't allow these rotation into the third dimension. Okay? Now, let's see here. Now we're ready to go back and plug this in to our previous. Okay, you should have it in your notes somewhere. Previously, I'll get them on the same screen. That. Okay, angular momentum about the mass center, that's that. Well, now we have a relationship for it. Angular momentum about the arbitrary point. Okay, so H naught equals IG omega k hat plus RG naught crossed into M VG. Okay, this is angular momentum about any point O. Again, planar motion is what's assumed here, right? Now, if one more thing we can say here is if the point O is fixed, meaning it's not moving, it's a fixed coordinate system here, then we can apply the parallel axis theorem, and H naught then becomes, all right, so if we apply the parallel axis theorem, oh, I gotta move this. Okay, that's fine. H naught becomes I naught omega k hat. Like, this is it. I mean, it's a very simple form for it. It's really that these two terms combine through parallel axis theorem, and we get that. Okay, this is our angular momentum about the fixed point O, where the fixed point becomes important. Okay, so this is any point. This is a fixed point. Okay. Now, I mean, you can think all we've done here is had a more general description of the kinematics, where we're now using angular momentum to do this. We want to now do something with it, right? Again, the goal here is to get to the equation of rotational motion, and we haven't gotten there yet. This is just describing motion still. What can we do with this? So let's, where we're at. So let's check in, right? Just an extended description of motion in terms of angular momentum. Okay, what do we do with this? We do with it we apply it to Newton's second law. Our general version of Newton's second law is sum of the forces externally acting on an object is not mass times acceleration. It's actually the time derivative of linear momentum. Okay? To get to the angular or the rotational equation of motion, it's an equation of rotational motion. So to get angular version of this description of motion, and Newton's second law basically in an angular sense, we then need to take the time derivative of angular momentum. So how do we do that? We basically take these relations as up here, right? This was the most general one, and we take the time derivative of that, okay? So we have what we had before. Angular momentum about any arbitrary point is the angular momentum about the center of mass plus the relative position from center of mass. It's really just the definition of it's the position vector of the center of the mass in the primary coordinate system crossed into our linear momentum of the center of mass. So to get to something that looks like Newton's second law, we come back up here and take a time derivative. Okay? Now we get time derivative of angular momentum is about O is time derivative of angular momentum about G, plus now we need a chain rule here. dg naught r dt. I think I said that in the wrong order. Okay, so that's just the derivative applied to the first term, plus rg naught crossed into now time derivative applied to the second term. And let's look at what we have here, okay? This term, let's start with the back one, right? This term, well, that's just the acceleration of the center of mass. And this term here is the relative velocity of the center of mass from g's perspective. I mean, this is also from g's perspective, but we can write this as, right, I mean, this is just the velocity of g minus the velocity of o. Right, well, okay. Now, before we go plug this in, we can now go to Newton's second law, but for angular sense, right? This is the time derivative that's going to be on the right hand side. What happens to the left hand side when you cross this, with the position vector? These become moments. Okay, so sum of the moments, and we saw this back in particle kinematics, or particle kinetics, I should say. Sum of the moments about some point O is now going to be this plus this. All right, so let's see. Let's talk about all of these terms. And we now have ability to well, let's talk about each of these terms, right? These first two terms here is what we had for particles. So this is the sum of the moments acting on a body, or if you had particles, right, about some arbitrary point O. This then is the time rate of change of angular momentum about O. That's what we had for particles. Oops, I think I was off the page there. Okay, so this is valid for particles, and a full description of how particles, about some point O act. We need this extra term here. This is an additional term for rigid bodies. And what it is it's a, to account for relative motion. Relative rotation, I should say. Okay? And so what we have here is, well, if point O, the point of which we're trying to take, do our analysis on, if that is also moving, right, then we have to add this term in there, okay? So what we're going to do is combine that guy, which we derived from our time derivative of angular momentum, into now our angular looking version of Newton's second law, and we'll get to our rotational version of Newton's second law in just, well, we got one more step to go. Let's just plug it all in, right? So this is now the this is good, right? We can just plug it all in. Let's just plug it all in. So we have sum of the moments about O equals, now we're going to plug in H naught dot, which is right up here. So this is going to be H dot G plus, okay, so in order to see this, let's just take a gander back up to here and rewrite this in a different way that'll be nice for plugging it in down here at this point. All right, so at this point we could write this as H naught dot minus, plus this term here, right? Plus one of these terms here. Plus, this is the second term. So we're going to take this negative V naught crossed into MVG and pull it to the other side. V naught crossed into MVG. Okay? That I pulled to the other side. Well, that equals HG. Then you have a term that's 0, right? VG crossed into MVG. Well, that's the same vector. That's the same vector crossed into itself. So VG crossed into VG, those point in the same direction. A cross product of two vectors pointing in the same direction is 0. So the only other term we have over here is plus RG naught crossed into m dvg dt. Okay, so now that's this whole term simplified. This now is the sum of the moments, all right? So we can, you know, to combine these two equations, this now is our sum of the moments, and it's just going to equal what we have on the right-hand side here. So plus rg from 0, or from O, crossed into the mass times the acceleration of g. And that is it. That is our rotational equation of motion. Rotational Newton's second law. That is, it's our rotational equation of motion. This is, we haven't assumed anything about point O, arbitrary O, and then we haven't also assumed anything about, or this actually works in 3D. Okay? So, to wrap this up, we will talk about special cases that, and then get a form of this, and then again we'll have a lot of examples, a big video next time doing examples of this long derivation here. But let's wrap this up by saying what's a simpler version, it's somewhat simpler. In fact, it might look a little bit more complicated, but we got like an, you know, a time derivative of angular momentum about the center of mass here. That's actually maybe not in the most usable form. So let's just give the form here for a couple special cases. Okay, the first one is, well, if we just make the assumption that we are in planar motion, what we have here is that hg is ig omega k hat, which we saw before. So hg dot, what can change here? Well, the omega, right? The object doesn't change its shape, so the moment of inertia doesn't change, but the omega becomes, the angular velocity becomes an angular acceleration with the time derivative. Unit vector doesn't change. So our sum of the moments about point O becomes the moment of inertia about the center of mass times the angular acceleration k hat. There's hg dot. Plus that relative position, well, it's just really the position from the point 2g crossed into the mass times the acceleration to the acceleration of the center of mass. Okay, that's like one step of just making the assumption of planar motion. Now, if we still assume planar motion, so let's say dot 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 up here, and so dot dot dot, and we do our analysis about fixed point. Oh, so look, it's this point is also fixed. What we are saying here is that well, we can go to a different form. Oh, I mean, you chose red up here, so I should follow that. Our angular, remember our angular momentum about point O is, then we can write it in terms of the moment of inertia about point O. Okay, and then the time derivative of point O is in that. And what this all stems from is a previous version of this, right, where we had our h naught up here, right, and we determined it this way, and we could actually just start from this relationship, yeah. And if it's fixed, right, then this is just 0. Basically, if it's fixed, v naught is 0. The naught point is it moving. So then we just get the sum of the moments is just this moment of inertia about point O times the angular acceleration. So that's a nice, convenient form if we can say our point of analysis is fixed, not moving itself. And then the third version that we could be using is what if the point O is the center of mass? So our point of analysis is about the center of mass here. And the simplification here, we're actually going to come up to this form here. This relative position vector is then 0 because they are aligned. the position to go from G to O, well, if O is G, then that is just 0. And so we have the sum of the moments about G is just this first term. Moment of inertia about G, angular acceleration, k hat. Okay, I'm not going to go any further with this. These are the I mean, we have a lot of equations here. We'll see how they apply to particular examples in the next video. And again, I have a lot of them, so it could be a long video, but that's to your advantage. Okay, that's it for this one though.